Good morning, ladies and gentlemen. No, it is not clickbait. This really is a Div 4 round. For those of you who aren't familiar, there was once long ago, back when dinosaurs roamed the earth and had not invented computers yet, a Div 4 round. It was pretty famous, and there were lots of questions of like, why do Div 4 rounds exist in the first place? Why do we need Div 4 when we already have Div 1, 2, and 3? How many divisions are there going to be? When's there going to be a Div 7? You know, thousands of questions. And this one, I'm pretty sure there's going to be at least one question asking you to print which division the round is, modulo 10 to the 9th plus 7. So this should be a very fun contest. It's supposed to be super easy. This is round 784, or Division 4 round number 2, whichever you'd prefer. Authors are Ericto, who is a super cool guy. I've done like two series collab with him. Elgo Talk. Pretty fun. I would recommend watching it if you haven't. It was a while back, but he's still a great guy. By Mike himself, the owner of Codeforces, and then some other people, Slavic G, Misanu, and Flamestorm. I'm not too sure who Flamestorm is. I'm not familiar with him at all. But Slavic G and Misanu are kind of living memes at this point. No, they do some good work. They write lots of problem sets. But given they're blue, they're a little unusual. So contest starts in 1 minute and 20 seconds. And for those of you who are new to this, of course, at the end, I'll be doing solutions to all of the problems. I'll be solving these in Java using Eclipse, which is currently my IDE of choice. Although I'm considering the possibility of using something else in the future. I've been trying it out on my own in a couple cases, and I'm pretty happy with what I've seen so far. But I guess we'll see. So this will be a Div 4 round starting in 48 seconds. I'm actively stalling here, and I appreciate this little heart-to-heart that we've had in the beginning of this contest. Before we start, I just want to say we have 26,000 people registered for this round. A lot of these people are blue and above, which means the contest won't be rated for them. So I think this is going to be one of the most significant like Codeforces stress tests in all of history. Like the servers are going to feel this one, and if it doesn't get delayed, I'll be very surprised. But we'll see. We'll see. All right, here we go. 5, 4, 3, 2, 1. Let's speed run this. All right. Let's see problem A. Along with the other 26,000 of us. Division. Codeforces uses these things. Giving a rating, print in which division the rating belongs to. Okay. Yep. Multi-test case. If n is less than 1400. This out. Division 4. Okay. Else if n is less than, what are the numbers? 1600. So this is division 1. Division 2, division 3. What's this cutoff? 1900. Okay. And then we should be good. All right, let's submit to A, and then we'll run samples. 444, oh, darn. What? Okay, so it's less than 1400 is this, it's less than 16. Okay, let's move on to problem B. If you submit and fail samples, you don't pay any penalty, so that's totally fine. Given an array of n elements, print any value that appears at least 3 times, or print -1 if there is no such value. All right. Yeah, sounds good. So we can say, there's a pretty easy way of handling this. What is this? The size and then the array. So int array A equals read array size n. And then we'll say int array count equals new int array n plus 1. And then this should be good. Okay, so we get -1, 2, 2, 4, looks good. Come on, give me problem C. So we got A. Pretty confident we'll get B. So we can see, given an array of n positive integers, we can do operations of the following two types. We can add 1 to every element with an odd index, add 1 to every element with an even index. Determine after any number of operations it's possible to make the array only even numbers or only odd numbers. Okay, so the parities of each parity have to be the same. So this is no, and then this is yes, and we don't have to print how many operations. This is pretty easy. All right, so we'll have our array A, an array of size n, and then we'll say for int I, okay, so we need Boolean array. Okay, so let's say Boolean even, odd, even, odd. All right, and then for int I equals 0 less than n, I plus equals 2. If a at I mod 2 equals 0, then even equals true, else even odd equals true. Okay, and then we want to do the same thing with starting at index 1, and then we'll say this is odd even, and this is odd. All right, and then sys out even, and even odd, or odd, even, and odd. This is the case. Then print yes. Wait. Print no. Otherwise, print yes. Okay. Looks good. Let's move on to problem D. Colorful stamp. A row of n cells is given, all initially white. Using a stamp, you can stamp any two neighboring cells such that one becomes red, the other becomes blue. Stamp can be rotated, okay. Yep. During use, the stamp must completely fit within the n cells. One possible example is a sequence blah, blah, blah. Okay. Given a final picture, is it possible to make it using the stamp 0 or more times? So, ooh, interesting. Okay, so it can be all white, that's fine. Or if there are continuous ranges, we can split them up. And then each range needs to have at least one of each. So that's possible, that's not, yeah, okay. So, yeah. So I think we'll do this a bit differently actually. We'll say string array input equals fs.next split on w. All right, then Boolean works equals true. Array. So if s dot is empty, then continue. Otherwise, we need to make sure there's at least one of each. So then for char c and s dot to char array. So Boolean has r equals false, has b equals false. If c equals r, then has r equals true, else has b equals true, and then if not has r and has b. If we don't have both, then it's impossible. So then works equals false. So if it does work, print yes, otherwise no. let's see if this looks right. Looks good enough to me. Okay, C and D are running. Move on to problem E here. And as predicted, Codeforces servers are having issues. All right, what do we get? We got one of them. All right, 2-letter strings. Given n strings, each of length 2, so there aren't that many inputs. Of lower than A to K, output the number of pairs of indices such that the I string and the J string differ in exactly one position. Okay, there really just are not that many things. Count the number of pairs such that the I string and J string have exactly one position such that they're different. The answer may not fit in this. Yep. Okay. This is actually very helpful. Okay, that's a good decision. Yep. Okay, so we can do it. All right. So let's say static int to int, then char array A, and then we'll return A at 0 times 1,000 plus A at 1. How many test cases? 100, so this should be fine. Sum of n is small. So then we'll say char array board, I guess I'll move char array n by something. And we'll read them all in. Okay. And then we'll say int array counting equals new int array n. So CS at 2 int at A plus plus. All right, so then long ans equals 0, sys out the answer. Now we have to figure it out. So for, we don't want to do it like this. We want to do it in the same loop. Okay. Yep. Okay, so then, cool. So then int array copy equals a.clone. And for int first 2 equals a, first 2 is less than or equal to k, first 2 plus plus. It's a char array, and then copy at 0 equals first 2. If copy at 0 is equal to a at 0, then continue. All right, so now we have all the cases it's different, and now ans plus equals to int at what is this? To int at copy. So this is copying the first thing, and then we need to reset this. Copy, well, we can just do this again. Okay, and then we'll call this second 2. This copy a 1, and then check this, and then we should be good. All right. Exception here, CS. This needs to be new int. We'll say 1,000. Okay, let's make this just 500. So we'll say 600 times 600. Should be fine. Way too big of a number. Oh, CS said this. Looks good. And they made the title 2-letter string, so we're extra sure not to get it wrong. Okay. Eating candies. How are we doing? Not necessarily bad. Okay. There are n candies put on a table from left to right. Each of the candies are numbered from left to right. Okay, the ith candy has weight wi. Alice and Bob eat candies. Alice can eat any number of candies from the left. She can't skip candies. She eats them in a row. Bob can eat any number of candies from the right. Of course, if Alice ate a candy, Bob can't eat it. They want to be fair. Their goal is to eat the same total weight of candies. What's the most number of candies they can eat in total? So we'll get all the prefix sums and then store the answer. Okay, should be pretty easy. So how big can the numbers be? Weights go up to this, so we need a hash map, but that should be fine. All right, so then we need our int array A, read array size n, hash, I guess we need long sum equals 0. That's fine. And then hash set of long, hash set goes into hash set. Okay, then for int I and a, we'll say sum plus equals I. Oh, we can always do 0, right? Okay, so set.add sum plus equals I, and set.add sum at the end. Well, actually, we probably don't need that. Yeah, we don't need that. So then sum equals 0 again, and we'll go from the right. So, and then we'll have an answer, I guess. So long ans equals 0, and then long full sum equals sum. All right, and then we'll say for int I equals n minus 1, it's greater than or equal to 0 minus minus. Sum plus equals a at I. And then we'll say ans plus equals, we'll say, so if set.contains the sum, that means you can get it from both the beginning and the end. And sum times 2 is less than or equal to full sum, then ans equals sum. Six out sum. Should be good. No, why? Ants. 10, 7, no, not 10. It is 10. Oh, the number of candies. Okay, this needs to be a hash map then. Okay, and then this needs to be, this is boring. Okay, so for 0 less than n plus plus, set dot put sum I, and then plus equals a at I, and then set dot contains key sum, and then we need ans equals set dot get sum plus n minus I. Six something 0 looks good. All right, good. E, F, G, and then H. All right, G. There's a grid with n rows and m columns and 3 types of cells. An empty cell denoted period, a stone denoted star, an obstacle denoted with the lowercase letter o. The stones fall until they meet the floor. Okay, so we have stones and obstacles. Okay. Stones fall until they meet the floor, an obstacle, or another stone which is already movable. In other words, this happens. Simulate the process. What does it look like? Okay, so things just keep moving down until they stop. So we can process each row independently, and then we should be good. Yeah, we just go up and then put stuff, just do a 2-pointer. You don't need to output a new line after each test. It's just in the samples to clarify. All right, sounds good. Looks good to me. This is G. That is G, okay. So first we have the height and then the width. So int h equals this, width equals this. Array grid, new, this is an int array. No, it is a char array. so height by something, and for int I equals 0, or it's like for int y equals 0, y is less than height, y plus plus. We'll say grid at y equals fs.next.dqarray. All right, so we've read in this grid, and then we can go x by x, so int x equals 0, x less than width, x plus plus. Then we'll say int next space equals 0, or equals height minus 1. For int y equals 0, y is less than height, y plus plus. This isn't true, we need it to go backwards, so y equals height minus 1, y is greater than or equal to 0, y minus minus. So if grid at y x equals an obstacle, then next space equals y minus 1. Else, if grid at y x is a blank space, then we do nothing, I think. Else, otherwise it's a rock. So then we'll say next space minus minus at the end, and then we need to move it. So then grid at y x equals an empty space. And then, oh, this is not quite, yeah, it is true. And then we'll say grid at next space x equals, what is it, a star? Okay. And then we do this for all the x's, and then we print it. So for int y equals 0, less than height, y plus plus, out dot print line, grid at y, out dot close. Why don't we compile grid at y? Because I don't have letters on my keyboard. My keyboard is all blank. Looks reasonable to me. Oh wait, yeah, I think that's fine. Submit G. Okay, we're getting all of them so far. Now we just have H left. Let and denote the bitwise operation or the bitwise OR. We're given an array of length n and a non-negative integer k. We can perform at most k operations in the following type. Select an index and replace ai with ai or 2 to the j. What? Where j is any integer between 0 and 2 to the 31. In other words, we can set the jth bit of ai to 1. Easy. Okay. I'll put the maximum possible value of these ands after processing at most k operations. So, yep, it's greedy. Can we do the biggest bit? Can we do the next biggest bit? Can we do the next biggest bit? So first we need to know how many elements are missing the biggest bit. So in this case, yeah, it's 2. 7, what is this, 0? We can do at most 0 operations. The answer is 4. 130, you can turn all the bits on, okay. Yeah, so we need an H, and here we go. K equals this, int array A, read array size n, and then we'll have long ants equals 0, sits out the ants, not too many test cases, right? We're good. Then for int bit equals 30. It's greater than or equal to 0. Bit minus minus. Then we'll say int missing equals 0. So for int I and a, if I and 2 to the bit is not equal to, or is equal to 0, then missing plus plus, and then if k is greater than or equal to missing, then ans plus equals 2 to the bit, and then k minus equals missing. And then we should be good. For big number looks good. Submit H. And stop the clock. All right, that's 1:37. How many minutes? It took me 22 minutes. Dude, I'm done. I'm done. Man, Dream Moon, how did he get these submissions judged? He's done in 19. 20th overall. Okay, yeah. So we got G. It's just a matter of time here for H. All right. Ooh. Did we beat Rainboy? Oh, maybe not. Yes, we did beat Rainboy. Let's go, ladies and gentlemen. We beat Rainboy. Ah, fingers of fire. All right, that was pretty fun. Let's just take a quick pause here. Watch what happens with this H. Who is this? Don't know who you are. Kiri 11? Who's Kiri? Don't know who Kiri 11 is either. Anyway, okay. Come on, how's this one doing? Are we in queue yet? Running a test case 5, 7. It's pretty quick, there's no way it's gonna be wrong. So after this, we'll have solutions to all the problems, in case you're interested. But I understand that lots of people have no troubles with these. We're gonna TLE, we shouldn't TLE. Yeah, we're good. All right, there you go, everybody. Thank you for watching. Where do we place? Geothermal again. Man, this guy, he is on fire. Well done, sir. Well done. Teaming is indeed unfair. You better not be teaming. Oh, no. Oh, no. Look at this. Oh, wait. Maybe it's legit. Could be legit. 2 submissions at minute 5. Guys. That's... no. Well, maybe H is doable in a minute. I don't know. That seems sketchy. Seems pretty sketchy. Purple Cran, well done. Okay, yeah, what place do we get? 41st place. Not bad. Top 100. I'm cool with that. 41st out of 26,000. I'm fine with that. Not bad, not bad. All right. Very cool, very cool. Let's talk solutions. Get rid of all of this. We'll start with problem A, and then we'll go through them. There's not going to be too much work on paper here because most of these don't require much thought. They're just pretty basic implementation. So these will go pretty quick, I imagine. So problem A, yeah, this is literally pure implementation. So you read the integer, and you want to check which of these 4 categories it is, and you print it. All this requires is if statements, and maybe a variable, I guess, and input. So yeah, here you go. So here is the thing. You read it, depending on these cases, you submit which division it is, and there you go. That's problem A. All right, so your problem B, triple. So we want to see how many elements, which element occurs at least 3 times in the array. But we can't do it by just doing 3 for loops. So 3 for loops would work, but it doesn't work in this case. Like, it would get the problem correct, but it doesn't work in this case. So what you have to do is there are a couple things. You can either use a hash map, or you can use just an array as like a hash map. So you can count for some element, how many times does it appear. And the way of doing that is you can have this array. This is like the count of each element, and you're guaranteed that all the elements are at most n. So this count array size is n plus 1 because the indices of an array are zero-based. They're zero-based indices. So if an array is of size 5, the biggest index in that will be 4. So if you want an array to be able to store elements up to 5, you have to make it size 5 plus 1, or size 6. So then for each of these elements in this array, for each element, we will increment its count, and then see if its count is bigger than 2, so if there are at least 3 of them, then we'll print it, and then we'll go to the next test case. Continue utter. Importantly, because I'm reading this whole thing in, I'm not skipping input here. So if you were reading the element in here, you wouldn't be able to do this. You'd have to like store an answer and then print your answer at the end. Okay. Yeah, so some of you might be interested in what does this fast scanner look like. This is just, it's the same thing as just a normal scanner in Java, except it runs a little bit faster. So we've got like buffered reader, new buffered reader, input stream reader, and then we got this. You can just pause and copy this if you're that interested. But it's pretty simple, yeah. And fast scanner is just how I do my input. The only difference is it's a normal scanner, except it runs faster, and it lets you do next array. You can read an array instead of just an integer. So you'd have to do a for loop for this without fast scanner. All right, that's problem B, triple. Let's talk about problem C, odd even increments. So given an array of n positive integers, we can do two different types of operations. So we can either add 1 to all of the odd indexed elements, or we can add 1 to all of the even indexed elements. And we want to know if we can make it so that the entire array is only even or only odd. So the first observation here is the only thing we care about is whether, whether an element is even or odd. We don't care about how big it is. So we can think about it as, instead of being an array of integers, we can think about it as being like an array of booleans, or an array of zeros or ones, right? So every element is either even or odd. And if two elements are both at an even position and they're different in whether they're even or odd, then it's going to be impossible. Because if you're both at an even position, you can only be changed with the second query. And if you change both of them, one will be even, one will be odd, you'll flip it. The other one will be even, and the other one will be odd, right? So you'll never make them the same. But if all of the things with an even index are the same and all the things with an odd index are the same, then if they match already, you're good. And if they don't match, you can make all of the even ones odd and do the same thing with the other parity. So yeah, that's the idea. We just need to keep track of whether all the even ones are odd and whether all the odd ones are even or odd. So we can do 4 variables. Are the even indices even? Like, is there an even index which is even? Is there an even index which is odd? And you get the idea. These are for odd indices. So we'll do 2 for loops. This one starts at 0 and we increment by 2. And this one starts at 1 and we increment by 2 as well. So this hits all of the even indices, or I guess if you start counting at 1, this would hit all of the odd indices, but I like thinking about it in a 0-based way, and it doesn't really matter because they're equivalent. So yeah, this just keeps track of, do we have any even indices, and do we have any odd even indices? And then same thing over here. And the solution is we want to do some binary logic. So this might be a bit unfamiliar to you, but this code is equivalent to, I'll write the simplified version. This is equivalent to if this, then sysout no. So these two are equivalent. This one's just a bit faster to type. So yeah, it's like evaluate this. If it's true, do this. If it's not true, do this. That's what's going on. But yeah, you can do it with an if statement too. And it's impossible if we have both even and odd things on the even indices, or if we have both even and odd things on the odd indices. That's the idea for problem C. All right, cool. Problem D, colorful stamp. So yeah, we've got some strip of paper with red, blue, and white values. Initially, everything's white, and then we can use a stamp which is part blue, part red, and we can stamp something, or we can turn it around and do red, blue. And we can overwrite things we've already stamped. So the key observation here is that anytime you have a white, that means it wasn't stamped. So we can split this string on all of the white pieces, and then we can look at just the parts that have continuous red and blue. And for one of those, it turns out it's impossible if it's all red or all blue, and it's possible in every other case. So here's kind of a proof of why that's the case. First of all, let's look at if it's all red or all blue, right? So you have some elements here, and you know you have to do at least one stamp, and you have to do some stamp last. So maybe you do this last, you do red, blue last. Well, you have both a red and a blue. So if it's all red or all blue, you're not going to be able to get it, right? You can't make a last stamp. So obviously it can't be all red or all blue. The only other case is, like, how do we choose it's possible otherwise? So if it has at least one red and one blue, that means there's some red-blue adjacent pair somewhere in the array. Now, we can do this one last, right? So the last thing we do is going to be this RB. Before it, we can figure out everything over here. We can make this like, so let's say we want to fill out the first element, right? The first element's R, we do RB. And now we want to fill out the second element. Let's say the second element is B, we'll fill out BR. Let's say it's red again even, then we do RB. And now we're left with this blue here, but we'll overwrite the blue when we do this one here. So from like last to beginning, we can do this. This will fill out 3 reds. And if we wanted this to be blue, we could just swap this. Right? And we do the same thing going backwards on the right. So we could do, if we want a red here, we could do BR. And then if we want a red in, that was for this space. If we want a red in this space, we could do another BR, right? So, and that ends up with a string that looks like this. Looks like R, 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 B, R, R. And we can get anything we want here, as long as we have at least one red, one blue. So that's the logic to solving the problem. To actually solve it, we just need to do this. So first we'll split on the W's, and then once we do that, we will look at each of the strings. So this will give us an array of strings where each string is like, if we remove the W, it gives us the stuff on the left, stuff on the right. And it's like removes all the W's and then looks at, if you split on all the W's, what are you left with? Kind of as it sounds. So we get that, and then we'll look at each one of these strings, and we want to see, does it have both a red character and a blue character? So we'll turn it into a character array, look through all the characters in a for each loop. And then we can say, if this character is an R, then we've got an R, and otherwise it's a B, because we've removed all the W's here. Finally, if we have both an R and a B, or if we don't have both an R and a B, then it's going to be impossible. So then we can't do this entire test case. And we want this outside the for loop because we need all of the strings to work, all of the things split by W's to work. If any of them are impossible, then the whole string will be impossible. That's solution to problem D. Okay, problem E, 2-letter strings. So we're given a bunch of 2-letter strings. There aren't that many. Each have, I think this is like the first 10 or 11 letters of the English alphabet. Yeah, and we want to know how many pairs are there, like how many AB pairs or IJ pairs, where the 2 strings at these 2 indices differ in exactly 1 position. So they're the same for the first one, different for the second one. Yeah, and you just print the answer. Now, it can be a very big answer, so you don't want to use integers. You want to use something like longs. And yeah, that's the idea. Okay, so how do we do it? Well, we'll just say, let's consider one element. How many of the things before us have differed from us in exactly 1 position? So we can convert, like to make this a little bit more easy to implement, we can convert a char array to an integer. So we'll say the first thing times 600 plus the second thing. You can notice that for any 2-character like strings, this will give you a different value. Because these ASCII values are somewhere between like 0 and 256, I think. Maybe 512, I'm not sure. But this will give you like unique values for every pair. So yeah, if it's like, if you divide it by 600, you'll get the first ASCII value. And then if you look at what's left after that, that'll give you the second ASCII value. So this lets us turn them into ints, and then we can use the same thing we used in problem A, or sorry, problem B, you might remember, to count how many of these we've seen before. So we'll look through all of these characters. Like first we'll read them all in, and then we're going to look through all of the lines they give us as input. We're going to make a copy of this one. And then we're going to say, okay, what are all of the things we could change the first character to? So we'll brute force what we change the first character to. It's going to be a character from A all the way less than or equal to K. And this might look a little weird to you, but incrementing this character is just increments the ASCII value. So if you look up an ASCII chart, A through Z are continuous. So let's just do this here. So yeah, we're going to brute force what the first character is. We'll set this in this copy. We'll set the first character to whatever we want it to be. And we want to make sure that we don't differ in 0 positions. So it does actually have to be different from this A here. So that's what this is doing. If it's not different, then we'll skip it. We'll go to the next loop here. But yeah, so let's say it's different. Then we want to see how many of these things have we seen before. So we'll add that to our answer. And then we do the same thing, but for the second character. And I won't go through this line by line, but it's the same thing, but just all for the second character. And then finally, we say, okay, we've seen this before, so for everyone after us, they can see us. The runtime of this code is, I think, 20 times n plus 600 squared. So it'll run in order n time. If you try and do this by looking at all pairs, that will be n squared. So for each of the n things, you'll look at another n things. So for each n, you add n to your total. That adds up to n squared. And in this case, n can be up to 10 to the 5th. So if you do an n squared solution here, your code will be 10 to the 5th times 10 to the 5th. That'll be 10 to the 10th operations, so 10 to the 5th times 10 to the 5th. Where's my times button? Times 10 to the 5th. Okay, so this is, you imagine 5 tens multiplied together, another 5 tens multiplied together, that's 10 to the 10th. And computers can do about 10 to the 8th operations per second. So we're asking it to do about 10 to the 10th operations. That means this will take 10 to the 10th divided by 10 to the 8th seconds. That's not 2. It is 10. Or it's 100. So this will take 100 seconds. And the time limit is 2 seconds here. So it's not going to work. Yeah, so 10 to the 10 divided by 10 to the 8, it's 10 to the 2. You got 2 tens left over at the top that don't cancel out. So yeah, doing the n squared here won't work. An easier way of remembering is just if n is 10 to the 5th, you can't do n squared. You got to do n log n or something like that. Just order n, something like that. Okay. Yeah, that's problem E. Okay, what else do we have? We've got problem F, eating candies, and problem G. All right, there are n candies left to right on a table. The candies are numbered from left to right. Yes. Okay. The ith candy has weight wi, and Alice eats some, Bob eats some. Yes, yes, yes. So you want to know what's the most candies they can eat so that they eat the same amount. Now, to do this, what we'll first do is see what are all of the possible different totals that Alice could get. And we'll do this by looking at all of the different prefixes. We're going to put these inside of a hash map, and then once we have them all inside of a hash map, we'll be able to look at all of the values Bob can get and see what's the biggest that Alice can get and Bob can get that in total use less than half the candies, or use less than all of the candies, or all of them, less than or equal to all of them. So that's how many you want to use in total. And then also you want the weights to be the same. So yeah, that's the idea. I guess we'll just show you the code here because that kind of explains it better than anything else would. So, or maybe we should do an example. Yeah, let's do an example. Okay, so we'll do this example here. So let's look at all of the prefix sums. So initially, Alice can get 0, obviously. So Alice can get 0, or Alice can get 2, or Alice can get 3, or Alice can get 7, or 9, or 9 plus 4 is 13, or 14. So these are all of the different values Alice can get. So we'll make a hash map with these values. So we'll have 0. If we have 0, then we get 0 candies. So I guess it'll be like 0 maps to 0, 2 maps to 1, and this is our hash map. 3 maps to 2, 7 maps to 3, 9 maps to 4, and you get the idea, and so on. Then we'll go in reverse order. So Bob will eat from the suffix. And we don't need a hash map for this. We can just iterate through. But if Bob does this, Bob will have, he'll have 1 if he eats this. Obviously, he can get 0, so 0 is an option. Or if he eats this one, Bob will have 5. Or if he eats this one, Bob will have 5 plus 2 is 7. Or this one would be 7 plus 4 is 11, and you get the idea. So we want to see, for each one of these, does it exist in the hash map? So we have a 0 here. The 0 does exist, so 0 is possible. Now we have a 1. Does the 1 exist? Well, no. There's no key in the front that's equal to 1. So 1 doesn't exist. Okay, now we'll try the 5. Does the 5 exist? No, 5 doesn't exist, so we can't get 5 either. What about the 7? Does the 7 exist? Yes, it does. So we get 3. So that means Alice will eat 3 candies, and Bob will eat 1, 2, 3 candies, the last 3 candies. So it's not necessarily just this times 2, because Alice or Bob could get the 7 and just 1 candy, so it might be just 4. But yeah, so Bob will eat 3 candies because we've looked at 3 so far here. All right, how is that implemented? So yeah, we have this array, which we read in, and then we have this sum, and finally we have this hash map, which we're using. So we're going to look through all of the prefixes. We'll store the sum of this prefix, and then we'll put it inside this set. We're going to put 0 in first, although that doesn't really matter. We can do it after as well. You'll notice I don't put the entire thing in the set, but that also isn't important. You could also have it like this, and it would work as well. Okay, so we're storing this full sum so that we don't have the 2 halves overlap. That's one way that you should get this problem wrong. So if the 2 halves overlap, then you say like, Alice eats all the candies, Bob also eats all the candies. Well, obviously they can't both eat the same candy, so that's not a legit solution. So yeah, that's what's going on there. But that's why we store this full sum. So I use it down here. I say if the number of candies Alice eats and Bob eats are the same, and in total they eat no more than all of the candies, then it's legit. Okay, yeah, so then we're storing, so Bob is going from the end to the beginning. We store this in the sum, and if Alice can eat this many candies and this doesn't overlap, then we store this as our answer and print it here. Okay, so yeah, that's the idea. Then we store it as our answer, and we print the best answer. So we'll keep overwriting our answer because we know it'll get better and better as time goes on. All right, that's problem F. Let's look at problem G here, fall down. So, okay, in this case, we have this grid. We've got a bunch of rocks, and we have some obstacles and some rocks that'll be falling and some empty spaces. And all the rocks are going to fall down until they hit something, either a stationary rock or an obstacle, which is always stationary. We want to know, after this happens, what does the grid look like? Now, first thing to notice is that the rocks just fall straight down. So you can imagine we split this at each x position. And each x position is totally independent on the rest of them. It doesn't care what the rest of the board looks like. This x position can be solvable just by itself. So that's what we're going to do. We're going to solve each x position alone. And when we solve an x position, we can look from the bottom to the top, and we can see, okay, what is this next empty space this rock would fall to? We can keep track of the next empty space. So we have to do 2 things. We have to either move the rock into the empty space if we see a rock, or if we see something that isn't a rock, we have to make sure we keep track of what this empty space will be for the next time we see a rock. So initially, the empty space will be on the very bottom, because a rock would fall to the very bottom. And then if we ever see a rock, the rock will fall into the empty space, and it fell that whole distance, which means everything above it was empty as well. So since the rock fell here, the next empty space will be right above it. So we'll have to make the new empty space for the future, it'll have to be 1 higher. We'll also have to move the rock there. Also, if we ever see an obstacle, we know even if there's empty space below this obstacle, even if there's a whole bunch of empty space, any rocks in the future won't be able to access that because they'll be stopped by the obstacle. So the empty space pointer has to be the obstacle plus 1. And that's the idea. So I can show you the code real quick. is we have this grid. We read in the grid. I guess this is like a two-dimensional array problem, so maybe a bit tricky if you're not used to 2D arrays. Yeah, we read in the grid. We've got this. And then we're going to look at each x independently. So yeah, that's what's happening here. We're going to go from 0 to width. We're going to look at this x on its own. And yes, so here's the idea. We store this next space, and then we go from the bottom to the top. There are 3 different cases. So either we see an obstacle, we see an empty space, in which case we do nothing, or we see a rock. If we see an obstacle, we just have to set the next space to the space above the obstacle. If we see an empty space, we can just do nothing. And if we see a rock, we need to first move the rock down. So we need to turn this space into an empty space, put the rock at the next empty space, and we need the empty space to move up one. And that's what happens here. And finally, we print the grid, and that's it. Yeah, another thing you could do if you wanted is you could just repeatedly move everything down a space if there's an empty space above it. And I'm pretty sure that would be fast enough. So yeah, because the bounds are really small. I think this was the easiest to implement though, so that's why I did it. It's also the fastest, so this is n squared runtime, which I think is nice and clean. Okay, we don't need that. Last one is problem H, right here. Maximal and. Okay, so we have an array of numbers, and we want to maximize their and the operation we can do is we can take the or we can set a bit of an element to 1 if we want, of any element, and that's one operation. So we can do at most k operations, and we want to know what is the biggest this and can be after we do all k operations. So the trick here is that the way binary works, and this is like an important observation for any problems that involve like maximizing some binary value, the biggest binary bit is bigger than the rest of them combined. Same thing's true in any other base. Like in base 10, if you have a number that's like 3 digits long, right? So it's got a thousands digit, it's got a hundreds, yeah, thousands, hundreds, no, hundreds, tens, ones, so 3 digits. Anything that starts with a bigger hundreds digit, no matter what the other digits are, if the hundreds digit's bigger, the number's going to be bigger, right? Because 100 is bigger than even 99. Anything you can do with just 2 digits, 100 is bigger. So the biggest digit, or the biggest bit, in this case, is the most important. Yeah. So what we're going to do is see, can we make this biggest bit a 1? If we can, we're going to do that. If we can't, we shouldn't spend any of our operations on this biggest bit, because it's going to fail anyway, right? So there's no use spending operations on it because we know it's going to fail. So we're going to see, can we make this biggest bit a 1? If we can, we'll do it. If we can't, we're not going to spend any more time on it. Then we'll look at the next biggest bit. Can we make it a 1? If we can, we'll do it. Otherwise, we can't. And yeah, that's it. The code looks pretty simple. Code looks like this. So we've got our n, we've got our k, we've got our array. We have our answer. We print the answer at the end. All right, so then we'll go through each bit. So we go from 30 all the way to 0, because there are 30 bits. Or maybe, yes, there are 30 bits. Okay, so we go through these 30 bits, and we want to count how many of these bits are missing. So we'll iterate through everything in the array. And this is a bit complicated, so I'm going to explain what this line does, because I imagine people watching this video are not super familiar with bitwise operations. So what this is saying here is I missing this bit? Is I missing bit? That's what it's saying. How does it do that? Well, one left shift bit, this is saying in binary, I want a 1 with bit zeros. So as an example, 1 left shift 0 is equal to 1, just a normal 1. Yeah. Maybe let's just do a big comment here. I'll explain it here. 1 left shift 1 this is equal to 1, 0 in binary, this is 2 times 1 plus 1 times 0, which is equal to 2. 1 left shift 2 is equal to 1, 0, 0 in binary, which is equal to 4. And that's the idea. So yeah, that's what's going on here. So if we want this number in binary, right, if we have like 1 left shift bit, we'll have like a bunch of zeros and then a 1 and then a bunch more zeros. So that's what this is doing. We have bit zeros at the end. Okay, and we want to see I is some number in binary, so maybe it looks like this in binary. And we want to see, does it have this bit or not? So when we take the and of two numbers, that's what this is doing here, we'll say, look at both of these. Do they look at all the bits they share, right? So the and of two numbers, it's a 1 if they share the bit, 0 otherwise. So here, they're both 0, so it's a 0. Here, 1 is a 1 and 1 is a 0. They don't both have it, so it's a 0. They don't both have it, don't both have it. Okay, here, they both do have it, right? They're both a 1, so this will be a 1. And then we have a bunch of zeros at the end. So the and of these two numbers, it's got a 1 in this position, which means the and isn't 0, right? This number is going to be, this is 32. This number is equal to 32. This number in binary is 32. So the and is not equal to 0, right? It's not all zeros. So we're missing, or so we're not missing, so this if statement skips, because it's not equal to 0. So yeah, so we're not missing this bit, but if this had a 0 here, right, if we have this, then the and would be all zeros, so it would be equal to 0. So then in this case, we're missing this bit. That's what's happening here. Okay, yep, that's your bitwise operation stuff. And then finally, at the end, we say, so k is the number of operations we can still do. So if we can turn all of these elements on, we want to do it. So we get this bit, that's part of our answer, and then we have to spend this many operations. It's natural to think, wait a minute, are we sure we want to? Right? What if we spend all of our operations here? We won't have any left for the future. Well, it doesn't matter. It's better for us to get this bit and not get anything in the future than it would be to not get this bit and get everything, because of the way binary works. Like the first bits are more important. The bigger bits anyway are more important than anything that could happen later on. So this is something we want to do. And then finally, we print the answer at the end. All right, that was the contest. I hope you enjoyed. I had fun. It was a fun contest. Very easy, but I guess that's the point of a Div 4, isn't it? So hopefully you enjoyed. Well done to Geothermal on the win. Good job to Purple Crayon as well. Solid performance. How long did it take me? It took me 22 minutes. So yeah, all right. Pretty all right speed run. Less than double Geothermal. So I'm happy with that. But yeah, you got to be really quick. There are some 0-minute solves here. Look at that. That's impressive. I didn't even have a 0-minute solve. I had a 1-minute solve. Because I got it wrong. Well, I guess even if I didn't, still 1 minute. But yeah, good contest. Anyway, thanks for watching. Have a great day. And I'll see you in the next contest, which won't be a Div 4. It'll be an educational round. And then shortly after that, we have a real round. We got so many rounds this week. It's great. I love it. Okay, awesome. Thanks for watching. Goodbye.